Hello students, let's dive into the fascinating world of aldehydes and ketones by exploring their physical properties. Imagine formaldehyde or methanol as a sharp-smelling gas at room temperature, while ethanol is a volatile liquid. But as we move to higher homologues, aldehydes and ketones become liquids or even solids. Their boiling points are higher than those of hydrocarbons and ethers, thanks to dipole-dipole interactions from the polar carbonyl bond. Yet, they fall short of alcohols because alcohols form strong intermolecular hydrogen bonds. This unique balance sets the stage for many interesting behaviors of these compounds. Now, let's compare boiling points more closely. Consider compounds with similar molecular masses around 58 to 60. N-butane boils at 273 Kelvin, methoxythane at 281, propanol at 322, acetone at 329, and propan-1-ol tops the list at 370 Kelvin. The message here is simple. Hydrocarbons and ethers stay lower because they lack strong polarity. Aldehydes and ketones rise higher due to dipole-dipole forces, and alcohols go highest due to robust hydrogen bonding. As we lengthen the chain, van der Waals interactions increase, which nudges boiling points higher. This trend is extremely important for predicting physical states in lab and industry. Have you ever noticed how acetone, a ketone, mixes freely with water? That's hydrogen bonding in action. Lower aldehydes and ketones, like methanol, ethanol, and propanone, are miscible in all proportions with water. The partial negative charge on the carbonyl oxygen forms a hydrogen bond with the partial positive hydrogen of water. However, as the alkyl chain grows, the hydrophobic part begins to dominate, reducing solubility drastically. This is why propanol dissolves readily, but hexanone shows much less affinity for water. So, solubility directly reflects the competition between polarity and hydrocarbon bulk. On the flip side, aldehydes and ketones are fairly soluble in organic solvents like benzene, ether, and chloroform. Why? Because dipole-induced dipole interactions stabilize them in these media. In fact, larger carbonyl compounds dissolve better in organic solvents than in water, simply because their long nonpolar chains find a better home in nonpolar solvents. Industrially, this property is exploited. Acetone, for example, is not just a solute but an important organic solvent itself. Think about nail polish remover. Its effectiveness relies on acetone's excellent organic solubility. Let's turn to something you've surely experienced, odor. Lower aldehydes, like formaldehyde and acetaldehyde, have a sharp, pungent smell that's often irritating. But as molecular size increases, the odor softens, becoming fragrant instead of harsh. Many naturally occurring aldehydes and ketones are central to the fragrance and flavor industries. Benzaldehyde gives the pleasant almond scent, vanillin provides the sweet aroma of vanilla, and acetophenone contributes to perfumes. So, the same functional group that stings your nose in small molecules delights your senses when the chain grows longer. So, to sum it up, aldehydes and ketones occupy a middle ground in physical properties. Their boiling points are higher than hydrocarbons and ethers but lower than alcohols. Their solubility in water is strong for small members, fading as chains grow, while solubility in organic solvents remains excellent across the series. And finally, their odor evolves from pungent to pleasant, finding uses in perfumes, flavouring, and even industrial solvents. Remember, all of these behaviors trace back to the polar carbonyl bond and its interplay with chain length. I hope this session helped you see how chemistry is not just formulas, but the science behind smells, solvents, and even the perfumes you might wear. See you in the next class, where we'll continue to uncover the secrets of carbonyl compounds.